Hello, I'm Hwang from IIIXR, and today I'm going to hold a seminar about imitation learning. This is the seminar abstract. First, I will help you understand the idea of reinforcement learning with examples. Then, I will explain how traditional imitation learning came about. After that, we will look at a paper called GAIL, which addresses problems in traditional imitation learning methods. Finally, we will go through the code together. What is reinforcement learning? Let's use Super Mario as an example. We get information from the screen and think about how to move. Then we can control the character. When we clear the game, we feel a sense of achievement. Translating this into reinforcement learning terms, it goes like this. First, we call the learner, such as Mario, the agent. This agent interacts with the environment. The information that the agent can currently get is called the state. In this example, it could be Mario's speed or the location of Goomba. Based on this state, the agent has its own policy on how to move. When the agent decided to move in one of the directions like up, down, left, or right, the environment responds by giving a next state and a reward. In reinforcement learning, the goal is to learn a policy that maximizes the total reward. In reinforcement learning, the data is called trajectory or a rollout. This means a sequence of information such as the state and action at each time step. Reinforcement learning works well when it's easy to complete the task or when there is a lot of successful data. But what if data is expensive? For example, think about controlling a helicopter remotely or driving an autonomous car in real life. If something goes wrong, it can be very costly. Next, problems happen when the reward function is complex. Imagine a task where an agent needs to reach a goal without hitting other agents. If the reward for avoiding collisions is too high, the agent might be too careful and fail to reach the goal because they are too busy avoiding each other. Imitation learning is a technique where agents learn to act like humans. Instead of directly writing a reward function for the task, it learns from demonstrations provided by experts. Here, a demonstration means expert behavior created by the expert's policy. For example, to train a self-driving car, you can bring in a professional human driver to show how it's done. And the goal is to find the cost function from the expert's trajectories. In many fields, such as self-driving vehicles and assistive robots, there is a need for agents that act like humans. However, learning through reward functions alone has become difficult to cover all the many and complex scenarios. This is why imitation learning has been proposed. Imitation learning includes methods like behavior cloning and inverse RL. We will look at inverse RL. Let's look at the formula together. The first part we will look at is RL procedure. Given a cost function, or in other words, a weird function, we aim to find the optimal policy. Here, H stands for entropy, and the equation is this. The reason for introducing entropy is entropy measures the uncertainty of the policy's probability distribution. Higher entropy means more policy diversity. This helps distinguish between different policies even if they have the same reward. In other words, it allows us to tell apart different policies that give the same reward. Here is the next part. When given an expertise policy, the goal is to find a cost function that maximizes the value for the expertise policy while minimizing the value for other policies. In other words, we are trying to find a cost function that says what the expert does is the best. The main drawback is that the reinforcement learning loop is inside the loop of optimizing the cost function, which makes the process slow. This involves finding the cost function, then using RL to find the best policy for that cost function and repeating this process. In 2016, GAIL introduced and NIPS skips these intermediate IRL steps. It achieves this by using imitation learning methods similar to GANs. To briefly explain GANs, given a generated fake image and a real example, the discriminator learns to tell the difference between the fake or a real, while the generator learns to fool the discriminator. Before diving in, various techniques are used to create a form similar to GANs. It might be hard to understand all at once, so I recommend reviewing multiple times and watching the reference videos at the end. First, we introduce the convex real regularizar psi. This is useful because it allows us to add prior knowledge about the type of real function we want to learn. Here, GAIL aims to calculating the similarity between the expertise trajectory and other policies through psi. To solve this issue, we use two approaches: occupancy measure and convex conjugate. Occupancy measure is a distribution that shows the probability of taking action A in state S under a specific policy pi. It is an important metric that shows how the system works under a given Polish pi. Using this concept, the cost function we want to minimize can be rewritten. The expected cumulative cost can now be expressed as the sum of the probabilities of taking each action in each state multiplied by the cost at that state and action. Occupancy measure can be found through the policy as shown in the equation above. However, we are looking for is the policy itself. Therefore, this paper changes the problem to finding the policy through the occupancy measure. Lemma 3.1 of the paper shows the following equation. In this equation, the denominator is the sum of the occupancy measures for all possible actions A/ in state S. In other words, it is the total probability of all possible actions being taken in state S. The numerator shows the probability of taking action A in state S. We have examined the equations for two cases, finding the occupancy measure given a policy and finding the policy given an occupancy measure. For a general convex function, the convex conjugate is defined as follows. This is a widely known concept. As a result, using this, we can derive a form similar to GAIL's, which is why we use the convex cost function. Now, using the occupancy measure and convex conjugate, we can rewrite the reinforcement learning equation given the cost function tilde c as follows. We can see that this equation has the same form as the original IRL equation we wanted to find. Let's quickly summarize what we've covered so far. Traditional IRL finds a cost function that optimizes the expert policy, then uses RL to find the optimal policy again. Now, the problem has changed to finding a policy that matches the expert's occupancy measure. We used the convex conjugate to find the occupancy measure. Finally, let's look at the psi function proposed by GAIL. If we look at the equation slowly, we can see that when the cost is far from zero, it has a low penalty, and when it is close to zero, it has a high penalty. The reason for using this function is that when you take its convex conjugate, it becomes similar to a GAN. Here, D is the network for deciding whether SA came from the expert or not. This is the algorithm. First, initialize the policy and discriminator parameters. Then update the discriminator weight and policy weight at the same time. The fact that discriminators and policies or are updated at once is different from existing previous imitation learning. Here is the experiment. GAIL, which uses a neural network as the cost function, outperforms FEM, GTAL, and behavior cloning. The blue one is the GAIL result. The final section is code. Thanks to the release of the code, we can focus on how the discriminator is used to see the flow. The discriminator is updated using the following formula. The exp ops and IIIXR are the expert observation and action, respectively. OBS and X are the current observation and actions that follow the policy. I said that the goal of reinforcement learning is find a policy that maximizes the cumulative reward. In the case of GAIL, the reward is the sum of the discriminator's output taken as a log, discounted by the gamma value. The calculated return is used to compute the advantage value, which is then used to update the policy pi. This idea is similar to using discounted rewards in traditional reinforcement learning. Then the complete code can be found at the following link. I hope this seminar has helped you understand the overall concepts of GAIL. Thank you for listening.